IoT hardware can be categorized into three common categories: microcontrollers, microprocessors, we also call a system on a chip, and then the other peripherals such as sensors, actuators, and other components. So these are the three distinct categories you are going to see when you are prototyping an IoT solution. So in this figure, you can see a variety of different components: touchpad, touch keypad, LED matrix, LoRaWAN radio, fingerprinter, a recording device, Bluetooth low energy, OLED display. So there are many components, over thousands of components you can buy off the shelf that are designed to do different tasks. But these are the three primary categories of prototyping hardware components. We already talk about microcontrollers from more conceptual and theoretical point of view. In this lesson, we are going to talk about from more practical point of view. So microcontroller is a small computer on a single integrated chip, less than sophisticated than a system on the chip. Most of the time, you are not going to see an operating system within a microcontroller. It is basically a fast running loop where everything you need to do within two loops of setting up, and then the loop that runs after that. Basically, you are looking at two different phases of programming. Microcontrollers are often used for ruggedized environments, which is designed to do one particular task, such as managing components within a car. So basically, you are not looking at a one microcontroller for the entire car, but each individual task will be managed by a single microcontroller. They could work on high temperatures and can withhold vibrations, and you can produce them in a very small size. Microcontrollers are supposed to run one single program. They could often store in read-only memory that does not get changed. And also, microcontrollers often low-power devices like 50 milliwatts rather than 50 watts compared to a traditional desktop computer. Microcontrollers are also small and low cost. Now I would like you to pause this video and watch the video I have put here to better understand about the microcontrollers. Throughout different lessons, we always talk about the system on the chip or microprocessors and microcontrollers and their differences, having operating systems and not having operating systems. But in here, I would like to give a little bit more concrete details about how they differ. So microcontrollers are dedicated for a specific task. Microprocessors can handle a little bit more generic purpose work, mostly supported by an operating system. So the operating system will handle which application get to run at what time. That is also a disadvantage we discussed earlier, that microcontroller, there's no multiple applications to move around. The dedicated application will be get access to the computation resources all the time. Microcontroller has a CPU, memory, input, output, and are present internally. In the microprocessors, memory and input devices are connected externally. Microprocessors are expensive, microcontrollers are cheap. Power consumption, microprocessors are high, microcontrollers are very low. If you are looking for a low power, always on device, you could also think about the microcontroller instead of a microprocessor. When you come to RAM, typically a microprocessor will have about 512 to 32 GB For example, one of the common latest Raspberry Pi devices have 4 GB memory. Microcontrollers have very little memory, could ranging from 2 kilobytes to 256 kilobytes. The newer versions might have more memory, as I said before. Throughout these slides, what I'm highlighting is the gap or the difference. So the gaps between the two segments or the classes or the categories of microprocessors and microcontrollers will remain for a long time. But these actual values might get updated. So both sides will have better performance or better resources over time, because manufacturers are putting more and more computation power into each of these categories. But the gap will remain for a long time, because there is a use for each category. You don't want to put a lot of resources into a task that only requires a small amount of computation, because it's a waste of resource. That means you have to increase the cost of a device or IoT solution. Because of that demand, there will be always two categories. The storage in the microprocessors, you are looking at from 128 gigabytes to up to 2 terabytes. In the microcontrollers, you have the flash memory. You probably have 32 kilobytes or 2 megabytes. The peripheral interfaces, the microprocessors will have access to a USB, Uart, high-speed Ethernet. Microcontrollers, you will have Uart, I2C, and SPI. In terms of the size of the registers, addresses, and data buses, the microprocessors are working on 32 or 64-bit address space, and the microcontrollers are working on 8, 16, or 32-bit address space. There are a few terminologies that might be benefited to get familiar with. The first one is the flash memory. Is an electronic non-volatile computer memory that allows to storage programs. You can erase them and also reprogram them. Typically, the Arduino sketches that you will be programming are stored on flash memories within microcontrollers. Another terminology is USB, Universal Serial Bus. Is the industry standard for connecting computers and peripherals. So you will be using these to connect your Raspberry Pi to your computer or your microcontroller to a computer in order to do the programming. Depending on the external peripheral, either during development phase or runtime, you will be seeing different types of USBs. So all these different types shown on the image are used in different settings. So it is useful to get familiar with these USB cables and their connectors, so you know which one to use. When you are programming, you might need additional adapters as well. Because if your computer doesn't support a certain type of USB connector, it might require adapter. So that is something you need to keep in mind. Each of these adapter and the cable type, there are specifications behind the scenes. You might don't want to memorize those because you don't have much of a choice. If the adapter is there, then you probably you need to use it. But make sure that if some of the data rates or data bandwidth is not sufficient to do some kind of communication, it might be worth looking at these USB cables, seeing whether they have drawing enough power or whether they have enough data bandwidth. Another important term is Uart. or universal asynchronous receiver and transmitter. We also call these serial ports. So these are used computer hardware devices for asynchronous serial communication, in which data format and transport speeds are configurable. But you need to make sure that you are configurable the both ends, not a single end. And then you are take a byte of data and transmit the individual bits in a sequence manner. So you send a sequence of bits, and then on the receiving end, they are put them back together into a single byte. They are widely used in both Raspberry Pi or single board computers or microcontrollers Arduino domain. So typically serial transmission of digital information, or as bits, through a single wire is less costly than parallel transmission through multiple wires. So that is why the Uart is widely used, and we also call serial ports. I have put 2 videos to explain how the Uart protocol works. Please go and watch these 2 videos to understand the protocol and the workings behind the Uart communication. I want to reiterate the fact that microprocessors and microcontrollers are not therefore to be replaced by each other. They are 2 categories. They have their own job. They have their own role to play within the IoT systems. Just because microprocessors seems to have more powerful computation capability, that does not mean that they are better than microcontrollers. So there are opportunities where microcontrollers is better, and there are other opportunities where microprocessors are better. So the real-world implementations of these microprocessors and microcontrollers that you come across in IoT are Raspberry Pi and Arduinos. They are quite different boards. We already discussed some of the common characteristics in earlier slides. In these slides, I have 2 videos that explains the difference between microprocessor and the controller from more theoretical point of view, and the other video, the actual talk about the Arduino and the Raspberry Pi, which is the concrete implementation of microprocessors and microcontrollers that you are widely used in IoT domain. Please go and watch these both videos. Let us now look at the one of the most popular microcontroller platforms, Arduino. Arduino is an open source electronic platform based on easy-to-use hardware and software. So the project started in 2005 and it grew quite a lot since then. There are a lot of tools and software frameworks being developed to help the Arduino developers to speed up the development process. Because of the open source nature of both hardware and software, the cost of development of the production of these Arduino open source platforms has reduced significantly. So that is why you can buy Arduino so cheap, as well as the other components like sensors and actuators. So the ecosystem around the Arduino is most of the time open source, which means you can get the schematics, and technically if you have the knowledge of manufacturing, you can go ahead and manufacture your own sensor components. So this is the Arduino IDE, the integrated development work look like. As you can see, it's a basically 2-loop system where you have the setup and the loop. Everything else you need to write yourself. But there are people who have been developing a little bit more high-level frameworks. Similar in desktop computing, we have like Java or Python. You write programs in high level. Somewhat similar, but not as sophisticated as frameworks. Because when you are writing a framework, the framework adds overhead, because frameworks are for general purpose. So the more you comprehensive the framework, it will add more overhead to the computation device. But the problem, this is not a problem in traditional computing. or even for single board computers like Raspberry Pi, because they have like 4 GB RAM and gigahertz of computation. But for a small microcontroller, every line of code matters, and then every kilobyte of memory matters. So that's why most of the developers who develop microcontrollers actually write their own code. So there are limited support available in the Arduino to make your life easier, such as reading data from GIP pins or other sensors and actuators. But there are little bit high level frameworks to make your life easier. If you look at like Groove sensors, where you can directly read sensors and actuators. So please go and watch the video I have put here from the co-founder of the Arduino, where he talked about the development of Arduino platform. As shown in this slide as well as the next slide, there are many different types of Arduino microcontrollers. Each one is designed for a specific purpose. So some are like entry-level microcontrollers, some are Internet of Things specific, where they comes with Wi-Fi by default, or maybe Bluetooth by default, or LoRaWAN by default. So there are a lot of different microcontrollers being developed to support different types of developments. So the philosophy behind Arduino is they are modular. So you get the board, the minimum basic board, then you can connect. If you want RFID reader, so you can connect an RFID reader. If you want a Bluetooth, you can connect a Bluetooth reader. But sometimes when you're connecting additional ones, they are not optimized as they are coming together. For example, if you take a Arduino, and then if you take a LoRaWAN module or a Zigbee module, and then you combine them, connecting them by yourself, it is less optimized than buying an Arduino controller which is inbuilt, which has inbuilt Zigbee or Bluetooth or whatever the communication module. So that is why there are a lot of different variations, where different combinations, the mostly commonly used combinations, are being implemented and developed. But if you cannot find one that you like, which satisfy your need, of course you can combine these modules. There are a lot of pins. You can see the black color pins, which you can plug different cables to it and then connect to whatever the component you are looking at. There are enhanced version here, and then you have the variables again. At the same time, there are older versions get discontinued or retired. So some of the Arduino microcontrollers you see in these slides might be retired by the time you watching this one, because there are a lot of new microcontrollers coming. There are big ecosystem. There are large number of people they call IoT developers or makers or hackers. They put together these prototyping platforms or different IoT applications. They come up with different ideas, and then when the Arduino as a company, when they see there are trends, they come up with their own solutions. And there are other companies who are also producing Arduino based their own microcontrollers. So there will be a lot of microcontrollers coming into the marketplace. So you should be able to look into the specification of each of these and pick the one that suits your particular IoT application. There's no one microcontroller is better than the other. It's just different specifications that targets different applications or audiences or deployment domains. Please go through to the Arduino website and browse through what are the existing Arduino microcontrollers, and then you can see what each of them can do. And please browse around to get a feeling about what are the available microcontrollers. It is important to note that Arduino is a prototyping platform. It is not for the production. Arduino helps you to prove a point, make a case, and see whether it is doable. Once you figure it out, then you need to completely redo everything in a production scale. You will need to go and develop your own printed circuit boards so you can miniaturize a lot of things. Arduino is somewhat generic, general purpose, even though you can buy a microcontroller that's specialized in a particular task. Still, it is a general purpose. So they are slightly bigger because it has input and output and other things that you need when you are combining different components together. But that is okay when you're prototyping, because the whole objective is to prove a point that your IoT solution works. So once you figure that out, then you need to properly manufacture them separately. So if you are new to Arduino, usually you'll be programming or start learning using an Arduino Kit. So there are 2 videos I have put about Arduino starter kits. So these are the commonly used starter kits to start learning. So you will be not using this starter kit in IoT labs. The reason is that these Arduino kits require a breadboard, and then you need to manually wire the cables by yourself. And then it's a little bit difficult if you don't have any experience on any kind of electronic, because you need to sometimes to put resistors in between components by yourself, and you need to identify what each cable or a pin does, and then a little bit of learning curve is there. Instead of this kit, we have chosen a kit called Groove, where all the resistors and cables are pre-packaged, where you need to clip them using a clip kind of a model, where you have digital analog slots, where you can connect a digital sensor to a digital slot and analog sensor to analog slot. But in the traditional Arduino, the basic kit, where everybody start learning Arduino, does not have that kind of clipping mechanism. You have to individually find out what are the pins and what are the digital pins and what are the analog pins. And then you need to combine different combinations and then put resistors to make sure that component doesn't get burned, putting more current through it. So you need to make sure what is the appropriate level of current expected by the particular component, and do everything by yourself. This is how the traditional people do things, especially if you are doing an electronic engineering degree. But because this is a computer science perspective, so we are looking at Internet of Things from a computer science perspective, it could feel like a little bit more learning curve. So that is why we avoided this in the IoT labs. But if you're really interested in going forward with the IoT development, it is better to get an Arduino kit by yourself and start learning them, because there are a lot of flexibility in Arduino kits rather than the Groove kit, where we use pre-packaged components and Arduino like boards. So in a typical Arduino kit, you will see a microcontroller. So this is the microcontroller you get, ATmega32. It has 20 digital pins and 12 analog input pins. And then you have 2.5 kilobytes of SRAM, 32 flash memory, which includes 4 kilobytes of bootloader, which is used to start the microcontroller. You also have a pulse width modulation pins, which is required by certain type of sensors and actuators. So in each of these kits, there are different components they have put together, LEDs and different motors and stuff like that. Please go ahead and watch the 2 videos. Here I am presenting a few more terminologies related to IoT development. So static random access memory, or the SRAM, is where the sketches. So when you write the Arduino code, it creates sketches. And then these sketches are created and manipulated, and variables are declared and run on SRAM. SRAM is volatile, which means that when you lose the power, you lose the data. Then we have Eeprom and flash memory. Both of them are non-volatile, which means the information persists after the power turned off. Eeprom stands for electronically erasable programmable read-only memory, where you can use them to store your programs. You will probably hear the term ATmega 328 chip, which is very popular chip in a version called Arduino Uno. Is one of the commonly used Arduino microcontrollers by entry-level or novice people. In that particular chip, you have 32K kilobytes of flash, where out of that 5K is used for bootloader. And then you have the SRAM for 2K, and then Eeprom for about 1K. Another type of chip is ATmega 2560. This one has a larger memory. So flash about 256 kilobytes, SRAM of 8 kilobytes, and Eeprom for 4 kilobytes. As you can see, each of them has different types of memory. So if you are looking for a larger memory, then this chip might be a best option for you. So that is why I mentioned earlier that there are a lot of different Arduino microcontrollers with different chips. So you need to pick whatever the microcontroller that best fit for your project. So you may have noticed that previously the Arduino Uno chip does not have much SRAM. So if you are planning to deal with a lot of strings, then you could end up with using ATmega 2560, which has 8 kilobits of RAM. So if you look at the I support the Cape Point project, that string requires 33 bytes in SRAM and 1 byte for the additional terminator. However, this doesn't seem to be a lot, but if you have only 2000 kilobytes, then 33 bytes is a reasonable number, especially if you are looking for large text to be displayed in a display component or large lookup table. If you ran out of SRAM, your program will fail in unexpected ways. It would be sometimes difficult to even debug to understand what is happening. There are a few things you can do to address the problem of lack of SRAM. So one thing is, if you are using an Arduino and you have another component like Raspberry Pi or cloud connectivity, then you can shift the data or calculations to the other component which has more computational power and reduce the workload on Arduino. And also, if you have lookup tables or large arrays, you should use the smallest data type as necessary to store the value. For example, if you take int, it takes 2 bytes, and if you declare as a byte, it only takes 1 byte. Of course, if you're using byte, that means you have a limited range of values you can store, but if that is sufficient, then you should not waste the int to store that. Another way to address this lack of SRAM issue is, if you don't need to modify strings or data while your sketch is running, you can store them in a flash memory instead of the SRAM. In order to do this, there's a keyword you need to use, prog mem. where it allows you to store strings in the more larger flash memory. Let us now look at the microprocessors, or they are also called system on the chip. Most popular implementation of these microprocessors are Raspberry Pi devices. So Raspberry Pi is again an open source hardware. It's a series of small single board computers which can be converted into full computers once we have the keyboard, mouse and the monitor plugged in. But this is just the computation device. The more latest version comes with the 4 GB RAM. Then there is a smaller version as well. You can see a USB-C port. You can see USB 2, 3, gigabit of Ethernet. There are two 4K display monitor ports, HDMI. So this is the highest standard Raspberry Pi at the moment. But what we have seen over the years is that every version comes much greater computational performance and capabilities than the previous one. And also we have seen another version called Raspberry Pi Zero, which is quite a small one, which is designed for small computational resource requirements in IoT projects. So again, just because a particular device has more computational resources, that doesn't mean that you have to choose that one. Because one, it could consume more energy, and also it could be more expensive. So when you're developing an IoT system, your responsibility is to pick the component that is sufficient to achieve the task. Of course, you might want to be a little bit more futuristic thinking, like whether you need some upgrades or more capabilities over the next few years, but technically you shouldn't pick and system on chip board which has large amount of resources than you actually necessary. Compared to Arduino, Raspberry Pi is also considered as a prototyping device, but it is itself is a fully fledged computer. So you can actually use it as a computer. There are some ruggedized versions that people have developed some casings that where you can put Raspberry Pi in, metal casings. You can deploy them in harsh conditions. And there are similar versions from different companies. There are something called Orange Pi. Then there's another one called Dragon board. And each of these single system on chip boards runs an operating system. There are Raspberry Pi operating system, but there are a lot of Linux variations. You can run on Windows. There's a Windows version for this one, Ubuntu version for this device, and then even Android version for this kind of Raspberry Pi. So please go and watch the video where they talk about the Raspberry Pi board in a bit more details. We have already discussed the differences between the microprocessor and the microcontrollers. But here we are going to discuss some differences between their implementations. Microcontrollers implementation of Arduino, single system on chip implementation, or the microprocessor implementation of Raspberry Pi. Raspberry Pi has an operating system. It's a mini computer which can run multiple programs. In the Arduino side, you can't run multiple programs. You only need run one program. Raspberry Pi is difficult to power from a battery pack. Arduinos can power from a battery pack. Raspberry Pi requires complex maintainers such as installing libraries and software, interfacing sensors. Arduinos are very simple to interface with the sensors and other electronic components. Raspberry Pi expensive, Arduino low cost. Raspberry Pi can be easily connected to internet using Ethernet port or Wi-Fi dongle. Sometimes Wi-Fi shields are embedded in Raspberry Pi. Arduino requires external hardware to be connected, like external shield to connect to internet. Raspberry Pi did not have storage on board. It provided a SD card for storage. Arduino do have very small amount of storage on the board. Raspberry Pi has 4 ports, could be varied depending on the version. Arduino only has 1 port to connect to the computer. That's it. The processor used for Raspberry Pi is RM family. The Arduino uses AVR family 80 mega 32.8p kind of processor. Raspberry Pi supposed to need to be shut down if you want to switch it off. Arduinos are just you can switch on and off at any time. There's no corruption would happen. The recommended programming languages are Python, but you can use C and C++ for Raspberry Pi. For Arduino, it's basically their own language of Arduino, which has C variation. So these are the common differences between Raspberry Pi and Arduino. However, depending on which Arduino you use and which Raspberry Pi you use, there could be some other differences as well. Both Raspberry Pi and Arduino are run on very low power compared to a traditional computer. But the difference is Raspberry Pi has operating system, so you cannot just plug off, or if the power interrupted, the Raspberry Pi could get damaged in terms of software, get file system corrupted. In Arduino, if there's a power cut, it will just restart. So both Raspberry Pi and Arduino has input-output pins. You can connect other peripherals using those pins. Raspberry Pi has 40 GPIO extended pins, which allows you to connect to sensors and actuators. Arduino also have 20 pins to connect external sensors and actuators and other components. The difference is Raspberry Pi has more standard connectors for external monitors, keyboard, USB, USB-C, Ethernet, and for an audio jack, which Arduino does not have. Raspberry Pi is much faster than the Arduino, perhaps like 40 times faster in terms of the clock. And Pi also has large amount of memory compared to the Arduino. Arduino have a few kilobytes of storage on board to store the code. In contrast, Raspberry Pi does not have any storage. Instead, it provides a micro SD port. Arduino can be expanded using external shields to support Wi-Fi, Ethernet, touchscreen, cameras, and everything. Raspberry Pi by default is a self-contained board. It has the most common communication input and output, but it can also be connected with touchscreen, GPS, and other electronic components through external shields. However, Arduino ecosystem is much more mature and strongly supported, so there are a lot of different components for Arduino than Raspberry Pi. For development, Arduino use Arduino IDE, even though there are some other up-and-coming IDEs as well. For Raspberry Pi, you typically use Scratch or Idle or anything that supports Linux. Raspberry Pi OS is a variation of a Linux operating system. As I repeatedly mentioned before, Raspberry Pi and Arduino is not something that you compare against each other. One type is best suited for a particular type of task. The other one is suitable for different type of task. For example, if you want to monitor the soil moisture and mail send me an email if there is necessary to water the plants. Perhaps you can use Arduino. So that is the best choice because it is connected to a sensor, and just send an email. But if you want to monitor the moisture and send me an email when the plants need to be watered, but you also need to check the weather report. So if there is no rain, then email me to water the plants. So that requires internet connectivity and accessing online APIs. So in this kind of situation, a Raspberry Pi, even a lightweight version of Raspberry Pi, such as Raspberry Pi Zero, might be more appropriate because Arduino is not necessarily designed to call online APIs. So likewise, Arduino is good at doing certain tasks very fast, like if you have any motors or if you have any robotic mobility kind of elements, any LiDARs, so autonomous movements, drones, then perhaps Arduino is good at reading sensor values and making decisions very, very fast. Raspberry Pi, on the other hand, is good at a little bit more complicated computation like video analytics or machine learning algorithms. However, you might also notice that if you search on machine learning, both platforms has the ability to perform certain amount of machine learning. If you search on TinyML, which is designed to be run on both Arduino and Raspberry Pi, TinyML, there's a microcontroller version, and there's a TinyML for single board computers like Raspberry Pi. At the moment, Google is the main developer. It is again an open source software framework, which we call TensorFlow. There is one variation for TensorFlow for desktop and cloud application. Then they have a TensorFlow Lite for Raspberry Pi or single board computers. And then the TensorFlow for microcontroller is another variant of the TensorFlow for Arduino. The performance are different. So when you are deploying a small machine learning model to Arduino, you need to strip down a lot of the complexities, which might impact the accuracy a little bit. But it is up to your choice to make the determination whether you want the full machine learning capabilities or whether the stripped down version, a lightweight version that can be deployed on an Arduino is sufficient. So you need to consider all the factors about what kind of components, where to deploy, what kind of energy requirement, whether need to be always on, and many other conditions before you come to a conclusion on what kind of primary computational device that you need to be employed in your IoT application system. At the beginning of this lesson, we identified 3 different categories: microcontrollers, microprocessors, and other sensor actuator display components. So we already talked about the microprocessor and microcontroller. So now we are talking about the sensors and actuators, displays, communications, and other components. In this slide, I have put a variety of different components which can be connected to both Raspberry Pi or Arduino. If you notice that each of these modules have a dedicated white 4-pin connector. So this connector comes with the ecosystem called Groove, which make it easier to connect. It has all the resistors and other electronic components embedded it, so there's no risk that no necessary for you to go and look for what is the input and what is the output current and then managing all the voltages and everything. These are all pre-produced, pre-manufactured, so you can just directly look for what type of pin it is looking for, digital or analog, and then go and directly connect and clip it. So you can clip out easily, so it makes it easier to process and make it faster to do the prototyping. To understand the available sensors and actuators and other components better, please go and watch this video. In the previous slide, I already introduced you to the Groove systems. It is a modular standardized connector that helps faster prototyping. Groove takes a building block approach to assembling the electronics. So compared to the jumpers and soldering, which require if you buy an Arduino kit, the one that I showed you earlier, which comes with the breadboard and all the cables, which you are responsible for managing all the voltages and currents and putting resistors in between. These are all pre-built, pre-configured. You only need to look for the right type of connector. Like here in the image, you can see D1, D2, IC2, I2C, Uart. Then there are sometimes analog sensors, A1A, A2, and then directly connected. So both Arduino and Raspberry Pi platforms have something called a Groove Hat, which you can plug on top of the board, and then you directly connect the sensors and other components into it. It makes the development much faster. So this is the kit that you are going to get for IoT labs. There are more details in this video about the beginner's Groove kit. Please go and explore it further in this video.